All right, in this video, we're discussing the p-value in the context of hypothesis testing. So the p-value is defined as the probability of obtaining a result equal to or more extreme than what was actually observed when the null hypothesis is true. So when we refer to result, we're referring to a test stat basically, because we collect a sample of data, right? And that's sort of our result of the experiment. And we summarize that sample data into a test statistic. So we're talking about basically what's the probability of observing a test stat that extreme or even more extreme if you assume the null hypothesis is true. And what it means to say you're assuming the null hypothesis is true is essentially that the true population mean is here on your drawing, let's say, and we're saying what's the probability, if that is where your true mean is, that your test stat would get this far away from it or even further, right? So that's the idea behind the p-value. All right, so let's talk about how you would apply the p-value approach to hypothesis testing. So basically, assuming that the null hypothesis is true, again, the p-value is the probability of observing a sample mean that is that extreme or even more extreme than the one you observed. And what that essentially means is that you basically put your test stat on the curve, right? And then you find the appropriate area associated with that test stat. So based on the definition of the p-value. So in the two-tailed case, essentially, you put your test stat on the curve and your test stat would either land here or on this side, right? And then you would find the tail area beyond the test stat. And then you would essentially double it, because the idea of the test stat being this far from the mean or further can happen in two ways, right? It can happen because you're this far from the hypothesized mean or further on the right, or this far from the hypothesized mean and further on the left. So there's essentially two areas that have to be calculated for the case of a two-tailed p-value. So basically what you do then is you just put your test stat on the curve, and let's say it was on the right, we'd find the tail area beyond the test stat, and then we would double that area, and that would be equal to our p-value for the two-tailed test, right? Remember, the two-tailed test occurs when HA has a not equal to sign. Now, in the case of a right-tailed test, we're talking about a scenario where you have a greater than symbol in your alternative hypothesis. Let's assume your test stat was on the right, then the p-value would essentially be the area to the right of the test stat. Remember though, your test stat could sometimes be on the left even when you're dealing with a right-tailed test, right? So a test stat doesn't have to kind of be on the side of the test, right? So if it's a right-tailed test, you would normally expect your test statistic to end up on the right, but that doesn't have to happen, right? So of course, if your test stat ends up landing on the left, the p-value is still the area to the right of the test stat. So don't let this drawing mislead you to think it's always a tail area beyond the test stat. Sometimes it could be that your test stat is over here during a right-tailed test, and the area all the way to the right is the p-value. So just remember, for a right-tailed test, the p-value is defined as the area to the right of the test statistic. Now, in the case of a left-tailed test, the same thing, but sort of in the opposite way, right? So if it's a left-tailed test, the area to the left of the test stat is your p-value. And don't forget, again, sometimes your test stat in a left-tailed test is on the right-hand side of the curve, which it still means that your p-value is the area all the way to the left, right? When your test stat is over here, it means your p-value is going to be quite large. It'll be something more than 50%. But if it's on the left-hand side of the curve, it'll be something less than 50%. But either way, the point is that wherever your test stat lands, the area to the left of it is the p-value for a left-tailed test. So it should be easy to remember. For a right-tailed test, p-value is equal to the area to the right of the test stat. For a left-tailed test, the p-value is equal to the area to the left of the test stat. And for the two-tailed case, it's just twice the tail area beyond your test stat, right? So if your test stat is on the left, you calculate the tail area, and then you double that answer. All right, so how do we use the p-value once we have it, right? So you'll have this sort of probability, or this, value you've calculated from your test stat. The way you make a decision is pretty easy. If the p-value is low, reject HO. So what do we mean by low? Well, this is just, first of all, a little poem to help you remember the rule. Remember, HO is really H sub 0 or H naught or the null, right? But the null doesn't rhyme with low. So just remember, it's if the p-value is low, reject HO. And what do we mean by low? We mean, hey, basically if the p-value is less than your significance level or less than alpha, then you can reject the null hypothesis. Obviously, if the p-value is not less, then you don't reject, right? Now, there is a scenario where some people are concerned about what if the p-value is equal to alpha? Well, that shouldn't happen very often, right? Because, the p-value is a continuous number, and, alpha is some fixed amount, like 5%. What's the chance your p-value is going to work out to be exactly 5%? Pretty unlikely, but let's say after you round it off to, 2 decimal places or something, you end up getting 5%. In those cases, it's just a marginal case, right? So you have to kind of decide as the researcher what you want to do. Basically, most people just report the p-value and let the reader sort of decide. Obviously, the whole idea is that the smaller the p-value, the more significant the result is, right? The more impressive it seems. Because of course, again, if it's the probability that you would observe another sample this extreme, right? Then of course, when it's very small, it's like, hey, this is a pretty unusual result. So it indicates something about the null hypothesis. Perhaps the null hypothesis is false then, right? So basically you reject HO when the p-value is less than alpha. Otherwise, you can say, don't reject, right? That's simple enough, right? So remember, this little poem will help you remember the rule. If the p-value is low, reject HO. Just say that to yourself when you're looking at a p-value, and it'll help you make decisions, and it's very simple.